So 8.2 says that the circuit diagram below represents a combination of resistors in series and parallel. The battery has an EMF of 12 volts and an unknown internal resistance R. And before 8.2.1, we are told that when switch S is open, right, here's switch S here, the reading on the ammeter, so we have some I, which is equals to 1.5 amps, right? And then 8.2.1 says let's calculate the total resistance of the circuit, right? We have internal resistance, so we cannot just use V is equals to I multiplied by R, right? We have to use EMF is equals to the current multiplied by the external resistance plus the internal resistance. The question says let's find the total resistance of the circuit. So we're looking for R external plus internal resistance, right? We have the EMF, it is given to us, and then we have the current, right? It should be obvious what we're gonna do now. So we're going to have 12 being equals to the current 1.5 multiplied by R external plus internal resistance. So we divide in both sides by 1.5, right? So we get R external plus internal resistance being equals to 12 divided by 1.5, which is equals to 8 ohms, right? So R external plus the internal resistance is equals to 8 ohms, and that's the total resistance of our circuit. And then 8.2.2 says let's determine the internal resistance of the battery, right? We know now that R external plus the internal resistance is equals to 8 ohms. So if we can determine R external, then we're going to be able to find R internal. But how can we determine R external? We know fully well that R external is equals to the resistance in series plus the resistance in parallel, right? So now let's actually analyze our circuit. So we have a positive terminal here and we have a negative terminal here, and then the current is flowing from the positive to the negative, right? And then at this point here, there won't be any current splitted, right? Because the switch is open. So the current just keeps on flowing, keeps on flowing, keeps on flowing, keeps on flowing. So basically what we have here is two resistors that are in series relative to the circuit, right? So R external will be equals to 3 plus 4, and then we're seeing that we don't have any resistors in parallel, right? So we're gonna have 0 here, and then that will just be equals to 7 ohms. So now we can say 7 plus the internal resistance is equals to 8. We're substituting R external into this equation here. So the internal resistance will be equals to 8 minus 7, which is 1 ohms, right? So the internal resistance is 1 ohms, and now we can do 8.2.3. 8.2.3 says let's determine the energy dissipated by the 3 ohm resistor in 3 minutes, right? So in order to determine the energy, so we know that the power is equals to the work divided by the change in time, right? So the work is equals to the power multiplied by the change in time. Every time when the question says let's find the energy dissipated, we're looking for the work, right? But then the power can take different forms. The power is equals to I squared multiplied by R. The power is equals to V squared divided by R. The power is equals to V multiplied by I. So depending on the variables you have, right, you use one of these equations to find the power. Clearly, for the 3 ohm resistor, we have the resistance, right, which is 3 ohm, and then we have the current, right? From the current we can calculate the voltage, right, and then use the other equations, but there's no need. So what we're gonna do here, we're gonna use this equation here, because we have the variables that allows us to do so. So now the work is going to be equals to the power. In place of the power, we're going to have 1.5 for the current, right? Squared multiplied by the resistance, which is 3, multiplied by the change in time, 3 minutes. But we know in physics we talk about seconds, right? Not minutes. So we're going to have 3 multiplied by 60. There's 60 seconds in a minute. And then if you punch that in your calculator, you're gonna get 1215 joules, and that is the energy dissipated on that 3 ohm resistor. Now let's do 8.3. 8.3 say switch S is now closed, right? Let's go ahead and close switch S. So here's switch S here, right? And we're closing it. When we close switch S, now the current is going to split here, right? At this point. So we're going to have a proportion of the current going in this direction, and then another proportion of the current going in that direction, right? And then how will each of the following be affected? Write down only increase, decrease, or remain the same. 8.3.1, the total resistance of the circuit. The total resistance of the circuit will decrease, right? Why am I saying so? Because if the current splits here, right, then the 2 ohm resistor and the 3 ohm resistor are now in parallel with each other. So R external will actually be equals to R in series plus the resistance in parallel, right? So this is going to be 4 ohms plus now the 3 and the 2 ohm signs in parallel with each other. So we're going to have 2 multiplied by 3 divided by 2 plus 3, and that is equals to 5.2 ohms. Clearly this is less than the R external we had initially, right? That R external we had initially was 7 ohms. So if we close that switch, the total resistance of the circuit will go down. And 8.3.2 says, how will the reading on ammeter A be affected? If V is equals to I multiplied by R, right? And we're saying that the resistance went down, then the current should go up, right? So the reading on the ammeter will increase. If you decrease the resistance, the current goes up. And now let's do last but not least 8.4. 8.4 is saying a conducting wire of negligible resistance is now connected between points X and Y. Before we read any further, let's just go ahead and connect X and Y. So here's X, and then let's connect X to Y, right? And then it goes on to say, as shown on the diagram above, what effect will this have on the temperature of the battery? Write down only increase, decrease, or they stay the same. What effect will this have on the temperature of the battery? So if we connect X and Y, right, we have reduced the resistance. Yeah, because now the only resistor that will be getting current is the 4 ohm, right? So we have reduced the resistance. What we can see first is that R external decreases, right? So R external will decrease. But then what is the consequence of R external decreasing? If R external decreases, then IT, the total current in the circuit, increases. If the total current increases, and we know that V internal is equals to IT multiplied by small r, right? We're saying that the current increases, the internal resistance is the same, so V internal increases, right? If V internal increases, the work done by the battery will increase, and as a consequence, the temperature will also increase.